Hello, everyone, and welcome to today's live broadcast, Controlling Terpenes and Cannabinoids in Flower and Extract, presented by Markus Roggen, Ph.D., Vice President of Extraction at OutCo. I am Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. We're delighted to bring you this educational web seminar presented by LabRoots. LabRoots is the leading scientific social networking website and producer of educational virtual events and webinars. Before we begin, I would like to remind everyone this event is interactive, and we encourage you to participate by submitting as many questions as you want, anytime you want during the presentation. Just click on the Ask a Question box located on the far left of your screen and type your questions into the drop-down box that appears on the screen. We'll answer as many questions as we have time for at the end of the presentation. If you have trouble seeing or hearing the presentation, please click on the Help Desk button located in the promotional board at the bottom center of your screen, or use the Ask a Question box to let us know you're having a problem. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located in the top right corner of the presentation window and follow the process to obtain your credits. Please join me in welcoming Dr. Roggen. I will now turn the presentation over to him.
So I welcome everyone to this talk. Thank you for joining in on my quick or hopefully enlightening presentation of the research we have been doing at OutCo about how we control terpenes and cannabinoids in our flower and extract. So to give you a background on extraction, we just were thinking, what actually is an extract and what should an extract do? So as I mentioned, it's the controlling cannabinoids and terpenes in flower and extracts. That means I want to be able to give to the customer or the patient the right cannabinoids they need, but also when I extract, I want to represent the flower. So often we see products that claim to be an OJ Kush or a GG, but they might not be what you would expect. So with that, we have to consider a few things. But let me give you an idea of what this talk will be about. We will talk about the backgrounds, we will talk about how we optimize our extraction, and we will compare and contrast a little. And I try to bring in a few other anecdotes and information snippets we found in our studies. So, what is an extract? So an extract is when a solvent removes something from a matrix. So butane extraction, CO2 extraction, ethanol extraction would be an extract. When people talk about a rosin extract or an ice water hash extract, that is actually incorrect, because from a chemical side, for extraction you need a solvent. Rosin is just a mechanical separation through pressure and temperature. And ice water extract is actually about the same. The water and ice cubes agitate the material and you collect the trichome. So again, it's a separation. But I just wanted to bring out these few inconsistencies or incorrectness in appointing terms in the cannabis industry, and I'd just like to point out small mistakes. But what is an extract? And for that, what actually is in the cannabis plant in the first place? So we all know about THC and CBD. We have heard about them often enough, and some people prefer the THC for the buzz. Others now claim that CBD has all the health benefits, but there's more than just two cannabinoids. We also might have heard of CBG, the precursor to all cannabinoids, all other cannabinoids, and then CBN, which is actually not a naturally occurring cannabinoid, but often used for sleep or relaxation. So, but there are a few more. Actually, there are over 140 cannabinoids at the last count. So just focusing, as I said earlier, on THC and CBD might not be the right method to offer the right product to the customer. But not only 140 cannabinoids, there are already over 200 terpenes identified in the cannabis plant. And terpene is what makes up the smell and the flavor of the plant. But terpenes are not just present in cannabis. They are present in basically everything that smells. Limonene is called limonene because it was first found in lemons. Beta-caryophyllene and humulene are also known in other plants. Beta-caryophyllene is actually what has this peppery taste. But then there are so many more terpenes of interest. And while it might be interesting, or it might be a good business thought of not using the terpenes derived from the cannabis plant, but using them from other sources like lemons, the problem there is that we can identify the first 10 or 50 most dominant terpenes, but as there are over 200 that in their combination make up the complex flavor profile of the cannabis plant, trying to recreate it is very, very difficult. So it might not be the best method to do this. But again, we're not yet done. There are also flavonoids that add to the complexity of the plant. And while flavonoids are right now not tested for in the cannabis industry, they do hold very interesting biological effects and should be considered when planning your grow process, your drying process, and your extraction method. But we're still not done. We have further compounds that are of biological activity and interest: alcohol, lactones, aldehydes, and it quickly becomes very complex. So we have so many molecules of interest. Maybe we have a method to present those to the patient and customer. So extracts might be a great way because just having flower limits you on consumption method and might go against the idea of a healthy patient when he then smokes a joint. So extracts might be the way forward. So extracts come in all shapes and forms, and they come from different processing methods, different application methods, consumption methods, or just interests of the patient. So what are those extracts used for? We use them straight up as a concentrate to inhale through heating, so dabbing or other forms of smoking. But they can also be used as a base to make further products like a sublingual tincture, a vape cartridge, a cream. So many possibilities, and they have to be considered depending on what the patient needs, what illnesses the patient have, or outcomes the client targets. So when I think about making extracts, I have to consider many different factors. And it was actually one of my first bosses when I entered the cannabis industry taught me to make the best extract. And I run into the problem that I don't really know what a best extract is because of all the problems I just mentioned. We have too many things to consider. So what might be the best for one patient or method or application method might not be the best for another patient. So, but there are still a few underlying principles that we all have to consider. And so if we think what is the best method, it's maybe the method that produces the most. But if I just think about weight as my benchmark for success, then if I juice some fan leaves, I get 60% yield. It's all water, but it's a high number on the yield side. So that might not be the best benchmark. So if I consider production costs, a PVC pipe, a lighter, and a cheesecloth should be really cheap, and my production costs are low, but I think open blasting like this in your backyard or blowing up your shed might not be the best method after all. So I think we should consider the extraction quality, that we represent the cannabis plant in our extracts. We don't want to make an isolate. We don't want to extract things that the patient is not in need of, but we also want to give a carbon copy of the plant if possible. So a last aspect to consider is the legal part. Different municipalities, different cities have different rules, and different states so too. We all know what Jeff Sessions' stand on cannabis is, but what does your local government think of it? So we are at OutCo are based in the county of San Diego, and while the city of San Diego was one of the first California cities to allow the manufacturing and sale of recreational cannabis, the county of San Diego decided to forbid this. So with further restrictions, while we are licensed for medical marijuana, we are only licensed to produce with CO2. We are not allowed to use ethanol extraction or butane. So therefore, in my case, I stick with CO2 extraction, and that's where I can present the data on. So how do I optimize? I have to consider a few factors what I am actually looking for. And I could look for yield per run. But again, yield might not be the best method, and per run is a batch process. So if I have a limited amount of material, that might be the right way. I want to get out as much as possible. But if I have unlimited material, or I have more than I might be able to process, I want to consider how can I produce the most per week. So that's a time factor here. And I'm looking for maybe high turnover. It is slightly different to yield per run. I can also consider cannabinoid concentrations. So how do I make a very nice pure extract or high in cannabinoids so that I don't have to make too many post-processing steps. Also, I can think about the terpene concentration or the content, because terpene is what gives flavors, what might be also a large influence on the entourage effect. So if I have a very flavorful, no terpene concentrate, it might not be what the customer needs. And then my favorite number is actually recovery. That considers of how much THC, for example, was in the plant to begin with, and how much do I recover at the end. Because if I make a 60% extract, but all of it is water or fats and chlorophyll, that doesn't help me. But if my plant that I put into the extractor has a 15% cannabinoid content, and if we have a 10-pound extractor loading, we therefore should get 1.5 pounds of extract out, of pure THC out. So if I now only hit a pound of THC, then I know I wasn't very good in my recovery. And I know that I can't get more than 1.5 pounds. So I cannot mathematically go over 15% yield if we align THC recovery and yields here. So recovery is a very good number to check your process. Okay, so how can I influence my extraction? I can, in this CO2 case, I can change the temperature, I can change pressure. I also can consider runtime. Flow rate of the pump is a very important, often overlooked factor, but also particle size. Anecdotally, we know that candied sugar does not dissolve as fast in your coffee as powdered sugar would be, and so the same should hold true for cannabis when extracting. So as an example, let's look at recovery in time. How does time influence my recovery? If I look at it, the longer I run the machine, the better my recovery is. But when I look at the graph a bit closer, there is actually a slight change in behavior. Initially, we have a straight line. So basically, the longer I run, the more I get out, and just run longer and I do better. And that is when the extraction is in its mass transfer phase. It can't go faster, but it doesn't slow down over time. But eventually it will. We see a diffusion phase later on in the extraction process. And at that point, we are entering diminishing returns. So when I run longer, I don't get out more or as much as I would expect. So if I would be on a recovery per run base, I would run longer because I want to get out as much as possible. But if I'm on a yield or a recovery per week, I should stop now because I'm going to diminish my returns. And also, this diffusion phase is, on the chemical side, not only lower yields, but also the extract constitution changes. When in the mass transfer, my extract at the 5-hour mark might be the same as the extract coming out at the 15-hour mark. When I enter diffusion phase, we see a change in composition. So there's less THC to extract, so it slowly still trickles out, but the CO2 starts to pick up other things. So chlorophylls, fats are now coming out. So I'm really putting myself in a bind if I were trying to push further. And this point of switch over from mass transfer to diffusion is about 80% recovery. So I'm already hinting you should really understand a lot of what is in your plant and what is your extract target. So loads of testing really helps here. Your local analytical lab will be very thankful, but depending on your operation size, you might also consider using your own equipment. So with the right staff in your company, it will pay over the long run. Okay, so this was our time example, but we can also look at particle size for our recovery. And as I already mentioned, anecdotally, we think there should be an effect. But actually, let's look at the data. So when we use the same starting material, the same amount of extractor loading, the same conditions on temperature, pressure, and time, so therefore they're not important in this example, and the only thing we change is particle size, we see that we get higher recoveries with smaller particle size. And it's an obvious trend here. There might be the fear that when the particle becomes too small, my extraction quality might go down because now chlorophyll can leach out quicker. But under operation condition, we have not seen that problem. Academically, yes, that is true, it can happen. But then we are talking about very small sample preparation volumes in an experimental setting. But if we're thinking of high throughput, large volume extraction operations, our case, we have a 10-pound loading per run, we won't be even able to grind that fine with a machine that would produce the grind in a timely fashion. We don't want to spend 5 days making a very fine powder to then extract it for a day. We need to be able to do this in an hour or two, and so those machines don't grind as fine, and therefore we don't run into problems. So how does our fine particles actually look? Here on the left side, you see some of our grinding experiment particle sizes, and on the right, yeah, that's how it actually looks when it comes out of the mill. And as my colleague once told me, we are definitely not in Kansas anymore. And I don't think Kansas even allows cannabis. So it's good that we are in San Diego. But as I just showed to you, if we change particle size, we extract more, so assumably faster. But if I also did my study on time, then I run into the problem that I change one factor and then the other factor is not valid anymore in my data. So I would have to rerun my time experiments after I run my particle experiment, and then basically go back and forth, and I try a third factor, and I keep on redoing everything every time. And I think we can do that more efficient. And to do that more efficient, we're using something that's called design of experiment. For that, we're looking at multiple factors at the same time. We can test the whole space of possibilities. And we can even see second-order effects that you will not see if you only change one factor at a time. And I like fast and efficient. I'm German, so that's what I went for. So how do we execute a design of experiment? And I go directly now to our execution and results, because while I really enjoy the underlying math and statistics behind it, when I have discussed that in a conference setting before, I had people leaving. I counted that as a win for myself, but to get now to the more interesting results, I will spare you this. If you have any further questions about the underlying math, please feel free to ask me afterwards, and I will provide you with all the necessary information. But let's talk about the execution. So we are looking in this example at pressure and time. And here I give you the upper and lower limits of the temperature and the pressure. And please be aware that I show you the temperatures in Celsius, because as a European, I still don't understand the Fahrenheit idea, even if it was invented by a German, but I think that's just the cruelty that we Germans like, and just push that onto you and you have to deal with it. I like Celsius. And then PSI for the pressure, which is actually now an imperial unit and not a metric anymore, but my extractor was built in the US, so it only gives me PSI. And it also gives you an idea here, changing between metrics and imperial units, how messed up the cannabis industry still is. We are trying to be better and become a real industry, but we're still stuck in the past in some areas and in our own ways. And I just take that as an example here. Okay, so when I want to look at temperature and pressure, I can think of a space, and I donate that here as our square. And I can just do 5 experiments donated by the points on this space to look at all possibilities, because the math that I spared you will then compute a surface that spans all possible combinations of temperature and pressure. And on the right side, I give you a table of all the experiments I run. We double the middle point, the C experiment, to also get reproducibility and the standard error. Because if I can't reproduce my results, then I don't have any option or possibility of optimizing anything if I can't trust my own experiment. So therefore, we had to do the C experiment twice. But I can also do this same method for the subcritical space, the liquid CO2, because I've heard so often, over and over again, that subcritical is better. Subcritical extraction is so much better. And again, I don't really know what the best is, but I know how to look for it. So these are the experimental conditions for our subcritical space. And to just give you a better idea of what I was testing or where I was testing in this space, I give you the phase diagram here in the middle. And CO2 gas phase is denoted as gray, the solid is the red, and then the liquid and the supercritical space is just there in the middle, and the squares with the point in the middle is basically the experimental conditions we tested. There might be a little bit of a slip. We didn't test gas phase CO2, just it was in that border region. Okay, so what are our results? As I promised you, after you did these 5 experiments and you use a little bit of math and a bit of programming, you see these surfaces. And surface gives you, in this case, the THC recovery in the supercritical space. And I also show you the formula that actually donates this surface. And when you look at it, that the factor for temperature, so XT, has a 15 in front of it, about 14.9. But pressure has a factor of 123. So we can already get an idea that pressure is far more influential on our recovery than temperature is. But both are positively aligned with recovery. So therefore, more pressure, more temperature, we get more yield, more recovery. And we can easily see that on the surface. We can also look at the same recovery surface for the subcritical conditions. And here the surface becomes a little bit more interesting. But the earlier ideas that pressure have the largest influence on yield and is positively correlated still holds true. It's now at 126, so slightly changed. Temperature is actually negatively correlated now with yield or recovery. But the second order effect of pressure temperature together is positive still, and therefore leads to this very interesting surface shape. But again, high pressure, high temperature in the subcritical gives us the best yields, recoveries. So for terpene concentration, that is something different now. First off, I'm not showing just the raw recovery. I'm talking about the concentration. So wanting a really light, terpene-rich, and in our case, cannabinoid-depleted extract, like I show on the left, was the goal of this optimization. And the formula, we are now getting really good at this math reading, is that both temperature and pressure are negatively correlated to the terpene concentration. So therefore, in the supercritical space, if we have just above the critical point, that might be the best condition for our terpene extract. We can also look at this on the subcritical space, and the surface now turn, but if you think back about the phase diagram, actually, it's pointing about at the same point in space on that phase diagram. It's pointing towards the critical point. So it seems that the critical point is what is critical for good terpenes. So with all this, we've now quickly, with a total of 12 experiments, so it was about a month work in the lab, and then a few long weekends on the computer for the math programming, we finish our optimization. But this is right now is all theoretical. It's math. With chemistry is what I like. But obviously my boss is asking me, is it the best extract? So let's look at it, because that's how you normally presented your extract in the first place. And these were some of the extracts we found, and I think they look somewhat similar to what most of you might have seen coming out of the CO2 extractor. I personally nicknamed them diarrhea, but I think we can do better. And one of the very interesting extracts that we found is these in the middle. They are actually 80% THC acid, straight out of the extractor. You have these dry rocks or powder that are just really high in THC acid. And this THC acid, that's what's actually in the plant, not THC. THC is decarboxylated after you smoke, or when you smoke it or heat it in other forms. THC acid is what is in the plant. So if you want to give the right representation of the flower, the acid form is what you have to go for. But it won't make you high. It's not psychoactive. But it does have healing properties. And I use healing properties here loosely. I'm not a medical doctor, so it's not mine to claim those. But we're working with doctors and nurses and the parents. We have formulated THC acid as a sublingual tincture for a 2-year-old epileptic patient because we really didn't want to make that child high, but we wanted to offer the potential healing properties of the cannabis plant, and smoking was not an option either. So having these THC acid-rich rocks were the way forward. Because we had already found in earlier tries that pure CBD wasn't working, and THC acid isolate is very expensive, and again, it is an individual molecule, and as I showed you earlier, it's the combination of multiple cannabinoids that make it interesting. So therefore, our whole plant THCA rich extract or rocks was the solution, and it worked. The kid has seen a significant reduction in seizures, and the mother reports very happily on the progress of the child. But for most of us, most of our customers, THC rich extracts, it's what everyone wants. We hear so often clarity counts. Vape cartridges flow better with the THC extract, not these rocks, obviously. So how can we make those? And with our optimized conditions, this is how our extract looks. This is how it looks straight out of the extractor. We did not winterize, we did not distill. That's how it comes out. I also think winterization is definitely not the solution anyway. Well, technically it is a solution, but process orientated. I don't see the point why you have to winterize something. And also, it's not a winterization. Chemically, it's a precipitation, but I'm not a fan. Sorry. Okay, going on. Now that we did the study of subcritical and supercritical, I can now compare and contrast, because earlier I said people said subcritical is better. So is it? Well, if we look at recovery, THC recovery, in the same time frame, because it's yield or recovery per week that we are after, we see a 20% point higher recovery in supercritical condition. Also, our terpene fraction actually become of better quality when we use supercritical. We have about 10% point higher concentration of terpenes at a markedly higher yield. And we can also look at other effects. So when we now have the whole data set, we can start digging into effects and behaviors on a molecular level. And it turns out that THC is more soluble in CO2 than THC acid. And I show you that both in a super and a subcritical space here, our starting material has a decarboxylation rate of 8 or 14% respectively. And when we extract only a short period of time, we raise this decarboxylation rate. So that is a strong indicator that THC extracted first, the THC acid stayed behind. Therefore, we improved our THC to THC acid ratio. But when we run longer to completion, then we come back to our starting material ratio, showing that we didn't see any further decarboxylation in the process and just kept the starting material ratios. And we can use that to actually affect the THC to THC acid ratio. So if someone would want a partially decarboxylated material, we can offer that thanks to our data sets. Also, we can look at CBD to THC behavior, because CBD, while it is an isomer of THC, so it has the same amount of molecules, the same amount of atoms in the molecule, it does behave different in CO2. It actually extracts faster, so it's more soluble. And again, I look at our ratios in the starting material after a short time and after a long time, and you see that the ratio increases to the favor of CBD, and then eventually comes back to the starting material ratio. So again, we can use this to adjust the ratio. So if a patient would need a 3-to-1 CBD to THC ratio, but in the flower you either get all THC, all CBD, or 1-to-1, genetically there isn't anything that does 3-to-1, you could either mix different strains, or we could actually take a 1-to-1 strain, adjust our extraction conditions, and then get the 3-to-1 ratio. So coming back to the title of the talk, we can control the cannabinoids and terpenes in the extract, thanks to all the math that I had to slug through earlier. And as a bonus point, decarboxylation of THC acid is actually faster than CBD acid. We have seen that trying to decarboxylate the flower in an oven, trying to decarboxylate the oil in an oven, or in other experimental setups. I'm still not sure why. I think it's a very interesting chemical problem. And I guess with some further kinetic studies or computational studies, this could be figured out. But for the producer, that's just something to consider. If you have your standard methods to decarboxylate THC-rich oil, and you now have a CBD-rich oil, those methods won't work. You need longer or higher temperature. So please keep that in mind. You can't just take your SOPs and take them from one process to the next. There are some stepping stones to always consider. Okay, so can we enrich minor cannabinoids? And yes, we can. It's an interesting and cool effect. If minor cannabinoids is what we are going for, CBG in this case, or maybe a THCV, that is a minor constituent of the plant, we can enrich here as well. So I've now showed you lots of result examples, but let's just overall think about this again of the title, where I also said controlling terpenes. So when we think about terpenes, as the last studies have shown, might actually be the best way of looking at strains. It's not the name, but the flavor that distinguishes a plant. So, and terpenes are the flavor. So when we go by a study from the Netherlands by Professor Hazekamp, he found that sativas, or what is said to be a sativa, are rich in monoterpenes, and indicas are rich in sesquiterpenes. So now then, for me comes the question as an extractor, can I play with it? And yes, we can. We can actually change, due to the different solubilities of monoterpenes versus sesquiterpenes, we can change the ratio. And so, boldly stated, I could take a sativa flower and turn it into an indica oil. And I thought that was a cool effect. I don't think that I can turn a sour diesel into a cookie or a tangerine flavored strain, but at least we can tweak a little. And I see this here not so much on the side of being able to customize strains, but being able to correct for any small variance in the grow. So if your indoor grow or greenhouse grow has small variations from harvest to harvest, you can adjust or dampen it with the extraction. Okay, so other extraction methods, and see, I made the mistake myself. It's a separation method if we think about rosin. And if we look at the recovery, and that was the number that really struck me, was we are getting 72% recovery. And I told you 80% is what we go for in CO2. So this is a really high and efficient high number and efficient process. And again, I like my math. So we used the same process of optimization for the rosin, and we found some interesting or annoying results that yield and quality are negatively aligned. So if you want a lot of yield, you get a low quality out. If you want good quality, you don't get much yield. So that might be a reason why it is such a connoisseur product. But again, we were able to play with temperature and pressure on the rosin, or temperature and time on our rosin press to optimize this. We also looked at ice water hash, and while it looks very nice and it's a high potency concentrate, we only got a 25% recovery. So we have to now think, what do you do with the material after the ice water hash separation? Can you use it in a second process, or can you optimize? We've tried a little, we haven't found much to optimize, so we have to think of a secondary process. But again, think about this for your own operation. Test your process throughout. Look at what's your starting material, what's happening through the extraction, what is at the end. Have you extracted everything or not? Test. Lots of analytics. I'm an organic chemist by training. I didn't think it was that cool, analytics, but it really helps your operations. Yeah, with that, I'm actually coming to a close, and I have to thank the supporting companies in this, because Apex was very nice to help us with optimizing our extractor. I call it now a Franken extractor because we had to make quite a few changes to the extractor setup, thanks to, or not thanks to, the optimization process and the math. I found that the extremes were the best conditions. So we had to be able to run the machine as at extremes, what it was designed for. So we had to add a few things to the machine to get that all running. And also, consistent particle size is what really makes your extract good. Consistent particle size will give you a consistent, fine, separated extract with a high throughput. And to do that, a kitchen grinder, a kitchen mill just doesn't cut it. You need a professional mill, and Fritsch was so kind to help us with a lot of expertise on their machine. And I even visited their production site in Germany. They can't play with cannabis there, but they grind a lot of hops, and that gets you a lot of beer and German beer. So it was a good trip. Let's say it was a good trip. But it's not only the manufacturers that helped us with it. Most important to the whole process is a great team. And for that, you need your colleagues with expertise to help you in all ways. And here on the right, you see Blake Kauerholz. He's my extraction manager. He was most instrumental in all the data I presented to you today. But Matt Zibiak, my production manager, or Taylor Tra in formulation, they play on all the other aspects of controlling cannabinoids and terpenes in the flower and the extract, or ultimately the product. And then on the left, I talked about analytics. And someone has to handle analytics. And someone has to be the annoying person telling you that this is not to standard, so you can't give it to your customer. And for that, you need a strong quality assurance person. And Chris Cortina has been instrumental in this process. So with that, I'm just at my last slide already. I thank you very much for listening in. I'm happy to answer all your questions that I probably wasn't able to answer in the short time frame. And I wish you a nice day.
Thank you, Dr. Roggen, for that informative presentation. We will now start the live Q&A portion of the webinar. So if you have a question you'd like to ask, please do so now. Just click on the Ask a Question drop-down box located on the far left of your presentation window. Type your question into the box that appears on your screen and click the Send button. We'll answer as many of your questions as we have time for, so let's get started. Our first question is, why is winterization not a good method?
So, as a chemist, I'm puzzled by the question, or by the process of winterization. So you extract something from the plant. So let's say you target extract something. So you have now your extract, and then you have to remove something from the extract. Why didn't you extract wrong in the first place? So that's why winterization really puzzles me. Also, it's not winterization, it's a precipitation. And then the third aspect, you use this very expensive CO2 machine to not introduce any other liquid solvent into your extract. But then you're using ethanol as a post-processing material, post-processing step, and then you have ethanol in your product. So, not a fan.
What are the limitations of your method and setup?
Still, there we go. Okay, so I'm back on. I was muted for a second, sorry. So the limitations are that we're doing good analytics, so we're using an outside testing laboratory to do the analytics. So the limitation there is that I have to bring that over, I have to wait for the results, so there's a little bit of a lag, so that limits my optimization. And then I'm using a 2000 PSI CO2 extractor with a one separator setup. There are machines that can do far higher pressures, which would probably optimize our recovery and yield per week setup. Also, with multiple separators, you can further separate your extract after the extraction in the recovery part. And then finally, we are limited to CO2 for law reasons. But every solvent has a different behavior on the cannabinoid solubility. So with other solvents, I should be able to give different representations of the plant. So I always try to stay true to the plant, but tweaking the ends is dependent on the solvent you use.
Well, thank you very much. I would like to once again thank Dr. Roggen for his presentation. I would also like to thank LabRoots for making today's educational webcast possible. Before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through June 29th, 2018. You'll receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That is all for now. Thank you for joining us. We hope to see you again soon. Bye.